Hello, everyone. I'm David Willis, and I am a teacher here at Lufkin High School, a science teacher, and I'm going to be with you today discussing gas laws and um, and their effects on different gases. So let's go ahead and begin with that. You should have a copy of these notes available. We will try and fill them in as we go, and we will check on them. I'll stop every once in a while and just check and see how you're doing with that. And we will work our way through this PowerPoint presentation. All right, so let's get started. And we will go ahead and press on. Let's see. So the first thought is, what do you think a gas looks like? And a lot of you are thinking, well, Mr. Willis, it doesn't look like anything. It's just open space. But if we zoomed in way small, and we looked at it, so let's say that I have a jar. Let's say that I just have a random jar, which let's make a nice little lid for it with some sort of, so it looks a little bit like a cookie jar. So let's say that I have a nice jar. It's clear, and we can see inside it. And you say that's if I just brought the jar in, opened it up here in the room, and then closed it again, it would have air from the room inside the jar. And you say that's exactly what it would look like, Mr. Willis. It would just be an empty jar. But it's not empty. If we zoom in super close, we would actually see little bitty molecules. Okay, now we would have to zoom in way more than microscopes, even down to the finest details of electron microscopes, in order to recognize or see any of this, because these are the actual atoms and actual molecules of gas that are bouncing around in this jar. And that's exactly what we would see, is that we would see that they would be bouncing around. Some would be going this way, some would be going that way. They would be banging into each other, a lot like billiard balls on the break, and bouncing all over the place, running into the wall and bouncing off. Okay, and so that is actually what the gas looks like at the microscopic, even submicroscopic, at the atomic level. And so that is the image that I want you to carry with you as we begin our discussions. All right. Let's see. Oh, I got to click back to the arrow, and let's see. Okay, there we go. And so this slide talks about what we had just discussed. That one model of a gas pictures a gas as made up of very small molecules moving around inside a container. And the molecules are so small that most of the container, and now this is true, most of the container is actually empty. In the sense that the only part of the container that's actually full is has anything taking up any space, is the actual little molecules. But if you remember back to that drawing that I made just a moment ago, and I'll sort of rehash it quickly. If I look and say how much of the space is taken up by the circles and how much of the space is open and empty, well, there's very little of it that's actually taken up by the circles, by the actual molecules. Most of it really is empty and open space. And so even though most of it is empty, it's not completely empty. Some of it is taken up by the molecules, which are zipping and zooming around all over the place. All right, so that's the model that I want us to maintain as we go through our presentation. Okay, and that may be new for you guys in terms of how you're visualizing a gas. All right, and that may seem odd. However, that is the current best understanding of the way the universe actually works. And that comes into something called kinetic theory. Remember that kinetic means moving or motion. And so this talks about the kinetic theory or the molecular kinetic theory of gases. It tells us that all particles are in constant motion. All right, and so all those little gas particles are zooming around all over the place. They're not just sitting there, continuously moving. A gas is mostly empty space, okay, which would be a vacuum or absolute nothing. However, it does have those tiny specks of matter, which are the actual molecules of the gas. The particles in a gas move rapidly and in constant random motion. They are not remote controlled or guided by anything in particular. They collide with each other and then bounce. Again, the best model that you may have available is the game of pool. On the break, you know how the balls go everywhere. And if there were no friction to slow them down and they just continued to zoom all over the table, that would actually be an excellent picture of what would be going on with the gas in a container. And they move in straight lines unless they hit something or until they hit something else. And all the collisions are what we call perfectly elastic. That is a fancy word that we use in physics to talk about the fact that all of the energy is conserved and is transferred from one to another and back again. So the energy is not lost or gained, but is in fact conserved. All right. And so that is the basic ideas of the kinetic theory. I tell you what, let's go back just for a moment, and let's look at this, and let's take a second and fill in some of our notes. Would you say that gas particles are close together or far apart? Okay, close together or far apart. Hopefully you got from our drawings and from our discussions that they are far apart. Let's see, I was looking for my highlighter. Oh, there we go. Okay, so hopefully you got that they are far apart. All right, and therefore the gases have, if the molecules are far apart, then that means that it is going to be low density. All right, so low density. Collisions between the gas particles are, what type? Anyone remember? That's right, elastic collisions. Okay, let's see, change that back to something a little more easily seen. Elastic. Gas particles are in continuous. Okay, now we need to look at number 3 for this one. This is a little tricky. Gas particles are in continuous, rapid, and random motion. Okay? And of course, kinetic energy is energy of motion. All right, there are no forces of blank or repulsion. If we're going to talk about repulsion, we also need to talk about attraction. Okay? Attraction, and I'll let you write that in. And the average kinetic energy of gas particles depends on the, and we have not really talked about this yet, but I'll go ahead and tell you, temperature. So the average kinetic energy depends on the temperature. And what you need to know from the molecular kinetic theory of gases is that at the same temperature, all gas particles have identical average kinetic energies. Now that's not necessarily identical speeds, it is identical kinetic energies. And so the gas molecules will actually have slightly different speeds based on their masses. All right, but the temperature is actually a measure of the average kinetic energy and is proportional to it. So as the temperature goes up, the energy goes up, and the motion of the particles will go up. As the temperature goes down, the energy goes down, and the motion of the particles goes down. And that should fit well with things that you have learned already. All right, so let's see. So let's clear the board on that one. And let's scroll down to around there, and we'll pick up there again in just a moment. So let's go back to our presentation. All right. So a gas is made up of many very small molecules moving around inside a container, and the molecules are so small that most of the container is empty. All right. Hopefully this is, we're just remembering things we've already talked about. What feature of the model is measured by temperature? Okay, so we've just talked about this. What part of the model would relate to temperature? And hopefully you're remembering that that is the energy of the model, okay, and specifically the kinetic energy. All right, what feature of the model is measured by pressure? Okay, and so when we think about that model, you guys are familiar with pressure in terms of the pressure in your tires or the pressure in a basketball or volleyball if you're playing sports. Okay, and you know that if you put more of a gas into the same size container, then the pressure goes up, and so that's actually going to be a measure of the density or of the amount of the gas that's in the container, or we could also say the volume of the container that's containing the gas. Okay, just a quick idea and little conversation about our atmosphere. Okay, our atmosphere divides into several different levels. The troposphere, and these two together make up the troposphere, and then we have the stratosphere. And almost everything that we are familiar with in terms of our everyday lives would happen in the troposphere. Even our weather is almost exclusively in the troposphere. Let's look at this a little bit, just to just to give you all the layers. Well, some of the layers. Um, so we have the troposphere, which is the first 11 to 20 kilometers, depending on how you measure. And this is where our weather occurs, where our aircraft fly, and and everything related to that. Then the stratosphere, which is where the ozone layer actually is, and so that actually protects us from a lot of the harmful rays of the sun. The mesosphere is between around 50 and 80 kilometers above the Earth's surface, very thin, very cold. Not to be confused with the thermosphere, which is actually warm. Um, it turns out that this is the very edge of space, and this is a lot of the solar radiation will warm the thermosphere, and then the exosphere is basically the edge of space. This is where we have the very edges of our atmosphere, and satellites are found. All right, so that's not going to be in your notes. It's just something a little bit interesting about our atmosphere. All right, so let's press on and see what else. Now, did you know our atmosphere, of course, you knew our atmosphere is made up of different gases. And if I were just to ask you which gas is the most abundant, meaning which one is there the most of in our atmosphere, what would you say? Would you say oxygen, since that's what we breathe? That is not correct. All right, it turns out that what's most abundant is nitrogen. Okay, and so it turns out that there is the most nitrogen out of all of them. And if you look, it's a huge majority. 78% of our atmosphere is actually nitrogen. 21% is oxygen, for which we are very grateful. It allows us to carry out respiration and have our bodies function in a way that we're familiar with. And then most of the remaining, like 2 or 3%, is argon, a very thin sliver of carbon dioxide, and then everything else. All right, if you're curious about exactly what that is, 78% nitrogen, almost 21% oxygen, almost 1% argon, only 0.03% carbon dioxide, and then it goes down from there, neon and helium. There is actually a little bit of ozone. Wow, you look at that. The ozone's incredibly small, and that's good. Ozone, while we need it to protect us, is not actually good for us. So it's good that there is not very much ozone in our atmosphere, and it varies from season to season. All right, something interesting to be aware of is that gases take on the size and shape of their container. If I had, remember earlier we talked about my bringing a jar into the room and opening it up, and that then it would be full of air. Well, what if I, instead of a jar, brought a cube or like a moving box, like a cardboard box? Um, or what if I brought a fishbowl? Or what if I brought whatever size and shape I bring? If I open it up to the atmosphere rushes in and fills it and takes on the size and shape of that container. And of course, the container size is a little bit flexible. If I have a movable top like a piston, if I take that and squish it down, well, then I still have the same amount of molecules, but in a smaller space. And so as my volume, my amount of space decreases, my pressure will go up and will increase. So we go from low pressure to high pressure by squishing it and reducing the space in between the molecules. And we'll talk in just a minute about why having the molecules in a smaller space causes that to be a higher pressure. All right, and gases are fluids. Mr. Willis, do you mean liquids? Is that the same as a liquid? No, it is not. Gases are fluids. A fluid is anything that can flow, anything that can be poured and can move like that. So here you see a liquid and it's being poured out in a way that you're familiar with. Here you can see a gas that's slightly heavier than the air, and so it is able to be poured out of this beaker in the same way that a liquid is. It's being poured out of this flask and filling this beaker and then overflowing and pouring down onto the counter in the same way that a liquid would. So gases are fluids. Fluid being a liquid or a gas, anything that can flow is a fluid. My street name is Fluid because I float. All right. Gases have lower densities than solids and liquids because the particles are more spread out. All right. So in that case, we see that there's actually, remember that density is about the mass per unit of volume. Okay, so let's just think about that for a moment. So the density is equal to the mass divided by the volume. Well, if we had a solid, this would all be completely filled in with molecules in the same volume. If we had a liquid, it would not be as tightly. It actually might be just as tight, or it might be just as tight, or maybe even a little tighter than the solid. So solids and liquids, though, would completely fill the space. Gases, lots of open space in between. Okay, and so the density, meaning how much mass we have in a given amount of volume, is much lower. All right, since gases are compressible, we can change their pressure by changing their volume, and they are compressible because of all this open space in between the molecules. So we can squish the molecules closer to each other, which would increase the density and would also increase the pressure. It turns out it doesn't increase the density very significantly, though, in terms of getting it close to a solid or a liquid. All right, what happens to the volume of the gases when they are compressed? Well, you can see that as this lid is pushed downward, okay. So just imagine some sort of force, maybe a hand, maybe some sort of machine. But imagine that there is some sort of force pushing down on that lid. As that lid shrinks down to this new level, what happens to the volume of the space inside inside our little glass jar? Well, it decreases, and so the volume decreases when gases are compressed. All right, let's see, we're embarking on a new topic now, kinetic energy. So let's go back to our notes and see what we can fill in from a moment ago. All right, let's see. Gases take on the blank and the blank of their containers. All right, size and shape. Remember that, or shape and size, whichever way you want to write. So size and shape of their containers. Gases are fluids because they flow. Now, did we decide that gases had a high or a low density? Very little mass for the volume they take up, so it is a low density. Solids and liquids will have a higher density. And gases are blank, meaning the particles can come closer together. We're going to say that they are compressible. compressible, meaning that they can be squished. All right, and when this happens, when we squish a gas, we will say that the volume decreases because the volume becomes less. All right, see, and I will go ahead and tell you that pressure is actually the force per unit area. The way we represent that is the amount of force divided by the area that it is spread over. In chemistry, this is referred to the force and the number of collisions of gas molecules with the walls of the container. So it is actually those. Let's see. I'll go back in just a moment. But it is actually those molecules hitting the walls which provide the force. So in this case, let's think about our two variables, force and area. So think about force and think about area. All right, I'm going to erase those. Let's go back just for a moment. Let's see, and go up. Okay, so let's think about force and area. So right now we have lots of volume, but we have this amount of area. Okay, and we have, a gas molecule running into the walls or running into the lid, the movable piston, or the bottom. We have these running into things every once in a while. Well, if I squish that flat, I still have the same amount of molecules, but in a much smaller area. Do you think that they're going to hit the edges more often or less often? Yeah, more often. And so they will absolutely be striking more often, which means there will be more force transfer since you have more molecules striking the edges. And that is why the pressure goes up for two reasons. Number one, mostly because the force goes up in terms of the number and frequency of collisions, but also you see that we still have the same area on the top and bottom, but we lost a little bit of area on the sides, and the area went down. So our numerator actually went up, and our denominator went down, and both of those things are going to serve to increase our final value. So there's that maybe got a little deeper than you needed, but the idea is that you have collisions more often, and so that is going to provide a higher or an increased pressure. All right, let's see if we got everything we needed to. All right, and then it says to draw a picture showing the relationship between pressure, force, and area. Well, I think that the previous picture here would be excellent. And you can just draw that real quickly and draw that at low pressure and high pressure. And just make a note out to the side that these are going to have less frequent collisions and these are going to have more frequent collisions. And maybe let's write less frequent collisions, less force. Okay, so I'll write that along with you. Less frequent collisions equals less force. All right? And then over here, write that more frequent collisions will mean more force. All right? And that will get our relationship between force, area, and you may even want to point out that because the piston has slid down, or because the lid has slid down in there, that there is less area. So you only have this much area compared to that much area, along with the top and the bottom, which stayed the same. All right, so that will give us a relationship between force, pressure, and area that the diagram asked for. So go ahead and pause the video for a moment and make your drawing, and then we'll be ready to continue. All right, we are ready to go. So let's press on. Um, the energy that an object has because of its motion is kinetic energy. And in a way, we've already discussed this. We said that, I told you that that related to temperature. So as thermal energy is added, your kinetic energy increases. And you know that as the temperature goes up, the speed of the molecules um, goes up as well. Now, not all molecules in a given quantity have the same kinetic energy. Okay, so we're talking about an average kinetic energy. I mentioned that earlier, that it's the average kinetic energy, and that it is proportional to the temperature of the substance. Proportional is a fancy word that means that they will change in the same by the same amount. Okay, and in fact, we're going to say they're directly proportional. And what that means is that if I have my average kinetic energy and I'm just going to use this, which is a symbol for proportional. Here's what that means, is that if your temperature goes up, then your average kinetic energy will go up. If your temperature goes down, then your average kinetic energy will go down. So directly proportional is just a fancy way to say that they change the same amount in the same direction. All right? And that is, we talked about that a little bit earlier, and this slide emphasizes it once again. All right. Ooh, which one of these represents normal body temperature? Which one of these would be closest to your normal body temperature? Now, I want to point out to you that we have Celsius as our unit, okay? And so that may, I don't know if that'll throw you off or not, okay? So take a look at that. All right. Now, most of you are probably familiar with Fahrenheit, which would be 98.6. 98.6 degrees Fahrenheit. And that, it turns out, is right around 37 degrees Celsius. So 37 degrees Celsius is right around normal body temperature. Turns out that 23 is very close to room temperature. That's about 74 degrees Fahrenheit. 100 Celsius is actually the boiling point of water. 212 Celsius is quite warm. You're not even cooking probably at that temperature. That's you're not cooking a cake, you're burning a cake at that temperature. All right. So it is still a temperature that you could broil things at in your oven. That would, but that would be quite warm. All right, let's press on. Okay, and so here's going to be our answer. We see that 0 Celsius is freezing, 37 is right around normal body temperature, and 100 is boiling, which is 212 degrees Fahrenheit, and that's where that 212 came in as a little gotcha trick. All right. Interestingly enough, there is an additional temperature scale called kelvins. And we will talk about Kelvin in just a moment, but I will go ahead and point out that it is 273.15 units higher than Celsius. Now, it turns out that 1 unit Celsius is equal to 1 Kelvin, and so when this goes up 100 from 0 to 100, Kelvin also goes up 100 from 273 to 373. And of course, in that spot, we also have 180 for Fahrenheit. So it's so those are not the same, but Celsius and Kelvin actually change by the same amount. All right, now in terms of upper and lower limits, there is theoretically no upper limit to temperature. As long as you can continue to add energy, you may continue to increase the temperature. The sun on the surface is around 6,000 degrees Kelvin, or around 6,000 degrees Celsius. The core is in excess of 15,600,000. I mean, wow. That is just super hot. That is hotter than the inside of your car on an East Texas summer day. That is just mind-boggling. So, so there is no theoretical upper limit. However, there is a theoretical lower limit, and that is a point when, remember that since temperature relates to motion of particles, there's a temperature at which all the particles should stop moving, and that is actually going to be what we call absolute zero. And that is what the Kelvin scale is based on. And so 0 Kelvin is absolute zero, and that is negative 273.15 Celsius. And at that point, we've never actually achieved that temperature. In theory, all motion would stop, all molecular and atomic motion, and that we don't know exactly what that would look like. So yes, absolute zero is 0 Kelvin. We don't say degrees Kelvin, we just say Kelvin. So it is 0 Kelvin, and it is negative 273 Celsius. Remember that Celsius is 273 degrees warmer than Kelvin. So if you take Kelvin and add 273, if you take Kelvin and subtract 273, you'll get Celsius. And if you take Celsius and add 273, you will get Kelvin. All right. Let's see. Let's continue our discussions about pressure. A gentleman named Torricelli was the first one to actually create a tool used to measure pressure, and that was a barometer, and that was in 1643. What he did is he took a tube that was sealed at one end, completely filled it with mercury, and then turned it over into a small dish of mercury. Well, some of it dropped out, creating a vacuum at the top. And as the atmospheric pressure changed, that is, as the pressure of the atmosphere got higher and lower, I don't know if you knew, but our atmospheric pressure doesn't stay exactly the same. It changes with the weather. It goes up and down. And as that changes, the level of his barometer, the mercury measuring column, would rise or fall. And so we call that measurement of pressure millimeters of mercury, meaning how many millimeters tall column could be supported by that amount of pressure. So gas pressure results from collisions of literally billions and billions of gas particles at any one time. And we talked about that, the forces that they are exerting on the walls of the container. And that is what creates pressure. And we mentioned that pressure is equal to force divided by area. And so if you take the area and measure the force, then you would have the pressure. All right, something interesting to know is that if I just have a balloon and I've just blown it up here in the classroom, you have molecules inside that are slamming into the walls of the balloon, but you also have molecules on the outside that are slamming into the walls of the balloon, and that is why it expands to whatever size it is. If I blow it up some more by putting some more air into it with my lungs, that puts a greater density inside, and so we have more pressure inside, and it expands. If we let some of that air out, then the outside pressure collapses it and makes it go flat. And so that is a little bit about how balloons work. So you have the pressure from the outside, and you also have, again, the pressure from the inside, and the balloon will increase and decrease in volume until the pressures match. All right, there are so many units for atmospheric pressure. You can have atmospheres, which is the pressure of one of our atmosphere at sea level. It turns out that is enough to support 760 millimeters of mercury. Remember that Hg is mercury, which is also 760 torr. Turns out that is also equal to a kilopascal, 100 kilopascals, a little over 100, which then if we bumped that 3 spots, you would get 101,300 pascals without the kilo. Remember that kilo is just a metric prefix. However, kilopascals are more common in terms of what you're more likely to see in chemistry. Let's see, 229.92. Okay, let's see. This is interesting. Let's see. So let's clear this off for just a moment. Oh, excuse me. 29.92 inches of mercury, not to be confused with millimeters of mercury. I was like 22.92 in mercury. What? So anyway, that is inches of mercury, and 14.7 psi, which again, psi is what we're used to having our tires at. And so if you think about that in terms of most of our car tires are around 30 to 35 psi, and so that would be slightly more than 2 atmospheres of internal pressure. And 1013 millibars. All right, so there are some units of pressure. Let's see if we need to record any of those on our other page. All right, so let's. Good. Instrument used to measure atmospheric pressure is called a. Do we remember that that is a barometer? All right, and all of these units are equal to each other. Oh, sure enough, and I do not remember. I remember, let's see, that 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 101.3 kilopascals, which is equal to, was it 29.92 inches of mercury, 14.7 psi, and, how many millibars was it? 1013 point something. Let's go back and check really quickly. 1013.2, and sure enough, that's 29.92. So let's go back and fill that in. 113 point, what did I say? 2, sure enough. All right, so 113.2. All right, I'm going to pause the video here for just a moment, let you write those things in, and then we're going to do a couple of conversions and continue our discussions. All right, thank you so much.